Hi everyone, the paper I'll be presenting is entitled Test Time Retrieval-Augmented Adaptation for Vision Language Models. Contrastive language image pre-training CLIP uses contrastive learning to learn aligned vision and language representations from paired images and texts. By creating a classifier from the labeled text, CLIP has enabled strong zero-shot prediction on various computer vision tasks that integrate human languages. Although CLIP has strong zero-shot prediction capability, its performance degrades when there is a noticeable difference between source and target domains. Domain adaptation is a method to alleviate this issue. The normal setting of unsupervised domain adaptation requires access to labeled source data and unlabeled target data before testing. However, we may not be able to access the source data due to privacy or data retention policies, and we may not be able to access the large amount of target data due to time-consuming data collection or constantly changing environments. Our solution is to use test time adaptation. It is more practical as we do not need to access the source data, and we only need to access the test samples one by one, which is the same as our real-world inference. Training-based test time adaptation methods use test samples to retrain the model. It can incur a high computational cost, which may not be affordable in some real-world or real-time applications, where the computational resources are limited. Our solution is to use retrieval augmentation. We first construct a test time database that stores important test information. Then, when a new test sample arrives, we will retrieve relevant information from the database to help make the final prediction. In addition, this method is training-free, meaning without gradient-based parameter updates, which makes it have a lower computational cost. The CLIP model was optimized to reduce the intermodal similarities rather than the intramodal similarities. This optimization process leaves a disadvantage that similar images in the vision space are not well clustered. As shown in the figure, the cosine similarity distributions of matched and unmatched image text pairs exhibit less overlap than those of matched and unmatched image-image pairs. This indicates that matched and unmatched pairs are more easily distinguishable in the multimodal space than in the vision space. Therefore, in addition to the vision space retrieval augmentation, we also added a multimodal space retrieval augmentation. Our method, test time retrieval augmented adaptation, mainly contains three modules. CLIP provides the base prediction, streaming mixture of Gaussian database SMGD module to store important test sample information into Gaussian centers, and a multimodal retrieval augmentation MRA module to retrieve important information from both vision and multimodal spaces. Streaming mixture of Gaussian database SMGD module aims to dynamically estimate the test distribution from streaming data. We assume the test sample embedding draws from a mixture of Gaussian distributions. Pseudo-labels are obtained from the CLIP prediction to determine which class it belongs to. The means and covariance of SMGD are updated with a momentum update of the past value and the new test samples value and covariances. In addition, we also update the entropy of SMGD, and we only update the means and covariance of SMGD if the new test sample's entropy is lower than the current entropy of SMGD. After building the database, we can retrieve information from database to enhance the prediction. Given the test sample embedding FT, the naive way is to conduct a dot product with the Gaussian means G. Since we also have the covariance, we apply Gaussian discriminant analysis to obtain its prediction. The vision space prediction is a combination of these two predictions. Since CLIP's joint vision text optimization does not explicitly optimize vision space similarity, therefore, we transform the Gaussian centers into a multimodal space using text embeddings. To do that, we multiply the vision space center means G with the text embedding and multiply the test sample embedding with the text embedding. Then we apply KL divergence to calculate the similarities between the new test embedding and each centers in a multimodal space, and trace the negative of the KL divergence as our prediction. Our final prediction is a combination of eclipse prediction, vision space prediction, and the multimodal space prediction. We compared our method with 4 training-based methods and 5 training-free methods. For training-based methods, co-op and co-co-op tune prompts using training samples, while TPT and diff-TPT tune prompts using test samples. In terms of training-free methods, including distribution-based, cache-based, and entropy-based ones. For distribution-based methods, MTA uses mean shift algorithm, while DN uses distribution normalization. For cache-based methods, TDA employs a positive and a negative cache. DMN compresses a dynamic and a static cache. Zero is an entropy-based method which sets the temperature of most confident predictions as 0 to approximate marginal entropy minimization. Our method achieves state-of-the-art performance on both cross-domain and out-of-distribution benchmarks, showing better results than both training-based and training-free approaches on average. From the application studies, we can say SMGD plays an important role, suggesting the effectiveness of modeling the streaming test data as a mixture of Gaussian distribution. SMGD and MRA also show complementary benefits. The consistent improvements can also be found on both VIT-B16 and ResNet 50 vision backbones. Detailed analysis of individual components of MRA shows the effectiveness of each component. Eta is the hyperparameter for balancing the historical and new information. Empirical experiments on UCF101 show that the optimal eta is 0.65, suggesting 35% historical information while 65% new information. When we can access to additional target domain streaming data, it allows us to directly estimate the target data distribution. We can then perform the same retrieval augmentation. It yields a significant performance boost without training. We also conduct more experiments using other vision language models, such as SIGLEAP, Align, and Flava. Our method shows consistent improvements and demonstrates the generalization of our methods. Thank you for listening.